Alrighty, let's do aromaticity now, as we kind of just left off of that of the tautomerization. Okay, so just to start off, the aromaticity. These are the hold on, let's do this. These are basically the rules. They follow a 4n plus 2 rule. What that literally means is the number of electrons follows that rule so that n is a whole number. Okay, it cannot be not a fraction, okay. What that means is 10 can work, right, because an n would be 2 in that case. So 4n plus 2 equals 10. N would be 2. Okay, that works, that's fine. If I did 12, 4n plus 2, 12, 2, 10 divided by 4, no. Okay, cannot have a fraction, no. That won't work. That's all it literally means. So that's the aromatic. So basically you can have like 10, you can have 2, like you can have just 2 electrons being an aromatic ring because n would be 0. N being 0 works. N being 0 works, just to clarify that. And then you can have the other numbers as well. Anti just follows a 4n rule. You can have multiples of them, so therefore you can have 4, 8, 12, 16, that kind of case, as long as it doesn't satisfy the 4n plus 2 rule, which it shouldn't. Non-aromatic, now, non-aromatic, again, when you're looking at the number of electrons, although the number of electrons might tell you that it could be aromatic or anti-aromatic, the difference, oh, sorry, I didn't mean to zoom in too much. The difference here is non occurs when an sp3 carbon is present. So that completely ruins you, because again, aromaticity is based off of forming sp2 carbons all around, right? Because you want the pi orbitals, and you want all of the electrons to essentially become cyclic and then overlap with each other in the cyclic space. So you have an sp3, or you have hydrogens competing for the same space. Those are the two conditions. Now, and with that said, an example would be like whenever you see a ring, actually, for this case, an example of this would be kind of what you saw in the group work, which was a really good example of it. It should be like this looking guy. Okay, and then we got this. Okay, in this case, the hydrogens that are inwards the ring, if it looked like just kind of 2 rings that were close to each other, right? This line separating them, that would have been totally fine. This would have been okay. But because you don't have a line that's separating the 2 rings, these hydrogens are essentially fighting for the same space, which is impossible because the bonds have to be inward, right? The hydrogens have to be within the ring, but you can't occupy the same space. They're basically like, they can't, like that's impossible. Both the bonds are trying to be like this, and that doesn't work. So that ruins your cyclic nature, right? So basically the molecule will contort and kind of destroy itself, and so that's where you lose the cyclic nature, therefore aromaticity. So that's that region. And an sp3 carbon is just like, you know, alkane carbons or basically just alkane carbons, right? Now, when I'm saying sp3, I want you guys not to be confused with the anions and the positive charges. For example, anion here, right, the negative charge versus this, we can agree that this is the sp3 carbon, right? So regardless of however many electrons count here, this is non-aromatic entirely, regardless, it does not matter. Here you have 4 pi electrons though, because another rule here, 2 rules. A carbon anion lone pair counts, okay, it counts to aromaticity, and it's considered sp2. Okay, so it's not considered an sp3 carbon. This is sp2, so it's okay. We can use this one. Sp3 on the bottom, you can't use that guy. You can't use them in terms of like aromaticity. You could use this though, and it would have given you 4 pi electrons, which would have given you anti. However, that's canceled by the fact that the sp3 exists, okay? The other condition is a carbocation. That is also considered sp2, but obviously because there's no lone pairs, none count. Those are the 2 rules, okay? So another example, let's say we have, I mean, you could kind of go back in here. Over here, we had like a negative lone pair. This total compound, in case you're asking the exam how many pi electrons would have contributed or do contribute, depending on whether or not they're non-aromatic, you have 1, 2, 3, 4, 4 times 2, 8, plus the 2 here, you have 10 electrons. However, the hydrogens that are trying to occupy the same space cancels that out, therefore it's non-aromatic, okay? In this case, you do have an sp2 carbo anion, but even though there's 4 pi electrons, it would have been anti, but the sp3 ruins it, non-aromatic, okay? Those are the 2 exception cases. The rest should just follow suit. For example, sometimes you'll see rings with heteroatoms, and what I mean by that is just basically anything other than a carbon. Remember, your goal is, and for the sake of just being simple here, just draw 1 lone pair inside the ring, 1 lone pair out. For these, just consider the one that's inside the ring contributing to the ring. The one outside, he doesn't, okay? He doesn't do anything, okay? So he isn't, basically just disregard this guy outside. If he's outside the ring, disregard. If he's inside the ring, regard for him. So 6 pi electrons, therefore he would be aromatic. And there's no sp3 carbons. Remember, sp3 carbons, not sp3 nitrogens or anything like that, carbons, okay? Focuses on sp3 carbons only. In the case of, you have exceptions as well. Boron and aluminum will be 2 exceptions, okay, with no lone pairs, but need 3 bonds, okay? Need 3 bonds. In that case, just be careful. This was just kind of like on the group work as well. For example, you have this guy, and then he's bonded to something. He's actually fulfilled, therefore you don't have any lone pairs that contribute, so you just have 4 pi electrons. Okay. Same thing with aluminum. Aluminum does the same thing. It's just because of their place on the periodic table and on the row in the column, they don't need to be satisfied with 8 electrons. So instead of being like this, they just need 6. Okay, they just need 6. These are just the 2 exceptions. In case you're ever seeing this on the exam, try not to trip up and miss these, because these 2 will be good trick questions. Those do not have lone pairs, and they do not need to be fulfilled by 4 bonds to them. Just 3. Okay, just 3. Good. So we've discussed that. Remember also, any sp3 carbons that are outside of the ring, you do not have to worry about them. They won't disrupt the ring's aromaticity. For example, these guys, they don't contribute because they're outside. Another example of where, I guess for the nitrogens as well, we could talk about the nitrogens. So we have a ring like this. Oh, actually, sorry. Here, and then we're gonna do here, here. Oh, wait, hold on, we can't draw. I can't draw. This. Okay, so in this case, you do have an outside lone pair. This lone pair that should have been kind of like, in the case that it would have been like this, and with the hydrogen involved, that lone pair that would have been inside is actually involved in this pi bond that's on the left, I'm sorry. So it's already involved in a pi bond, so this guy counts, these 2 other bonds count, so you have 6 pi electrons, and I don't count the ones on the outside. Don't worry about the ones on the outside, okay? Just don't. And then 6 pi aromatic. Another example, this dude, say for example, let me give you, hold on. He's like this, and then we should have fulfillment, like, no, hold on, should be a 5-membered ring. Okay, we'll do this. Okay, remember, nitrogen can have a lone pair in this case, and it is because its formal charge would be 5, so 1, 2, 3, 4, 5, and it's fulfilled that way. That's why there's no positive charge on it. This case, inward, inside the ring, count him. The bond that would have basically shown a lone pair for the nitrogen outside here is fulfilled by a hydrogen. So, you know, you don't have to worry about that because there's no lone pair there. So don't worry about that. Now you have 6 pi electrons, aromatic, okay? So that's in the case of heteroatoms. Sulfur follows the suit of oxygen, just kind of a chemistry thing, really. There's nothing much else to that. And yeah, now that you understand that, that was kind of a brief overview, but remember that inside the ring, the electrons inside the ring, if you draw them, they contribute. If they're outside the ring, they do not contribute. And again, on the exam, it could ask you, oh, how many pi electrons contribute? Like for example, here, you have 10 electrons that could contribute. However, your sp3 carbon, not this one, I'm sorry, your overlapped H's, disregard that. They basically destroy your aromaticity, and then you basically make it non-aromatic, okay? So that's the key there. And sometimes you'll be asked, what's the lowest energy structure? This has popped up on exams. Essentially, if you are aromatic, that is the lowest energy status. And that the reasoning behind that is because if the compound is aromatic itself, it's stable and it's in its lowest energy state because aromaticity has a lot of resonance conjugation and it's most stable there. So aromatic will stay aromatic. in the sense of the lowest E structure. This is usually like part C on the exam or even on the group work if you're trying to reference that. And then if it's anti-aromatic or non-aromatic, they automatically are non-aromatic. And the reason for this is because if you kind of remember back to these guys and then the big octagon with the tetrene, or no, sorry, I'm saying that wrong, but it had 4 alkenes. Regardless, these guys actually twist out of formation and they become like super chair kind of convoluted, making it non-aromatic. Okay, so just understand these are the lowest energy states. If you've identified as aromatic, it'll be aromatic in its lowest energy state. If it's anti or non, it'll be non-aromatic in its lowest energy state. So for the sake of the exam, yeah, good. Now we go to bases and acids. So these, the key for these is you just have to think back to what do bases and acids do. Bases will attract hydrogens, acids will release them, okay? So for example, I'll just do basic. Now the rule is, whenever you're doing these, your rule of what you want, so favored outcomes, is you want to gain aromaticity, you want to maintain it. Secondly, so first is gain, the second is maintain, third is lose. You do not want to lose aromaticity because you lose stability, okay? So this, do not want. This is the last resort, you do not want it. Now, this is the rankings though. So say if I have 2 compounds, one gains aromaticity, one maintains it. The one that's more basic or acidic, this applies to both. It's just obviously you have to be careful with what you do to the hypothetical products to make, and what I'll explain what I mean by hypothetical is you want to gain more than maintain, therefore the gain is more acidic or basic. If I had between 2 maintains, neither, doesn't matter because they're both the same. If I had between one gained and one lost, the one that gained is more acidic. If I had one between one that maintained and one lost, the one that maintained is more acidic or basic, okay? This applies to both basic and acidic. Now, the only difference is that whenever you're doing your problems, say for example, it says more basic, and we're gonna use this example, okay? So this is just nitrogen, and we have a lone pair inside here, and this is more. So which one is more basic, right? So out of these two, 1 or 2, and we're gonna draw the other one. Now you need to establish from the very first start, you need to establish are they aromatic or not. So in this guy, we have a lone pair that contributes, we have 2 other pi bonds, so we have 6 pi electrons. This guy's aromatic, okay? And then we're gonna make the hypothetical later. This guy, we have an outside lone pair, but we have a lone pair that's contributing to a p orbital already because he's in an alkene. Therefore, you have 6, 1, 2, 3. This guy does not count. You have 6 pi electrons. This guy's aromatic. Now, they're both the same. Now, the key is the hypotheticals. Hypothetically, because you're basic, you're going to attract hydrogens. So in your hypothetical, you're going to essentially make protonated versions of this, okay? So just to be safe, protonate your hypothetical, deprotonate for acids, okay? So hypothetically, I'm going to protonate the nitrogen because he's the only heteroatom that can be basically protonated, in this case because he has a lone pair that's able to take on a hydrogen. In that case, he becomes like this, and he becomes a carbocation. Now, I'm sorry, not a carbocation, but he has a positive charge, not a carbocation. Sorry, I don't want to confuse anyone. In this case, now you only have 4 pi electrons, and now this is anti, because 4 is just kind of following the 4n rule, is anti-aromatic. That's the hypothetical. Do the same thing for the other guy, and see what happens to the aromaticity. Okay. Boom, and then you want to do, this guy stays here. So as you can see, the outside lone pair took on the hydrogen, and the outside lone pair we don't count anyway. So nothing happened to the aromaticity other than literally nothing happens. It just stays the same. So aromatic still. Now, which one is more basic? The one that essentially either gained or maintained, right? In this case, I have lost, I have gained, or I'm sorry, I have maintained. I apologize. I have maintained. I have maintained. Therefore, he is more basic. And why I'm circling the top, this is the hypothetical. Remember, you would just hypothetically protonate this nitrogen, okay? Hypothetically, you're just protonating that guy. But you need to go back to the original compound and circle the original. Do not circle your hypothetical on the exam because that is incorrect. You go back to the original after you've done your hypotheticals to determine what lost, what gained, etc. Okay? And then basically the same rule applies for the acidic. So let's just say, for example, more acidic. And again, you need to go by this ranking list on the very top. Gain is better than maintain, which is better than lose. Lose is the worst. You don't want to lose. I mean, because stability and, you know, just how it is. Acidic. We'll just do an acidic example. Acids now, remember, for the sake of this, I just want to show you guys something. Now, you saw this on the group work, and hopefully this will be seen. Now, although you would say, oh, this is an sp3 carbon, so it couldn't be aromatic anyway, okay? But remember, you're working with a hypothetical scenario, so it's okay for these questions. It's okay. For the more acidic ones, it's okay if you have an sp3 and you're like, oh crap, well, it's not going to be aromatic anyways. Is this like a trick question? Well, no, because you're looking at hypothetical scenarios, so just think of it as if it's a hypothetical, okay? So we're going to work out this problem. This is a 7-membered ring, so it's kind of weird looking, but yeah. So keep working with it, hypothetical. Now, determine whether or not it is aromatic anti from the get-go. Beginning one. Is it aromatic? No. 4 electrons, therefore it's anti. This guy, 6 electrons, therefore it's aromatic. Hypotheticals, right? Hypotheticals. Now it's different though because it's acidic. Acidic, deprotonate, okay? Deprotonate. Remove one of these guys now. So remove them. And you're going to do that basically for anything that asks you for acid. Just remove one of the hydrogens. And a key note, a little tip. Sometimes you'll see lone pairs. Lone pairs that are free usually are the basic, so they will take on hydrogen. For the acids, you'll see usually that there's extra hydrogens, therefore you're going to take them away. Okay, that's just a little kind of shortcut trick, but it's not always foolproof. Just be careful. You've removed this. This becomes a carbocation. Remember, carbocations are still considered sp2. Okay, they're still considered sp2. Therefore, they're still able to be used, but you don't really change anything here because it's 4 pi electrons, and you have I'm sorry, actually no, hold on. Good. Let me draw this one out as well, just for the sake of being just want to be comparative here. Oh, hold on. Okay. Gosh, 7-member rings are really weird, but we're working through it. Okay. I'm sorry, not a carbocation, an anion. I apologize, an anion. Because essentially, you would break that bond and it goes like in towards there, right? Sorry, yeah, that makes sense, hopefully. Yeah, because you're going to deprotonate, and then this bond becomes a lone pair, an anion. Remember, anions are sp2. Therefore, they can actually contribute. So you have 4 from 2, 2, and then another 2. So therefore, you have 6 electrons, and you have an aromatic. Okay, aromatic. So you went from anti to aromatic, so you've gained here. This side. Now it's 6 pi electrons, then you've gone to removing one, and we're going to keep that as inward, negative. I would honestly, for this guy too, just for the sake of it, keep these inward because it makes your life easy. If it's in, contributes to the ring. If it's out, it doesn't. So put them inside the ring so you do not get confused, and it's easier for you to understand which one's aromatic, which ones aren't. Remember, lone pairs outside of the ring, not aromatic. Inside the ring, can contribute. I'm sorry. They outside the ring do not contribute. Inside the ring do contribute. Okay. Yeah. Sorry. But hopefully that's a clear distinction. In this case, it's 8 electrons. Therefore, it's a multiple of 4. So it's anti. Now I've gone from aromatic to anti. I have lost aromaticity. Therefore, gaining is best. Losing is worst. So this guy is more acidic. I go back to my original and I circle. Sorry. I go back to my original and I circle which one's more acidic. In this case, it is that guy because he has gained aromaticity versus lost, like in this guy. And remember, these are hypotheticals. So the sp3, you can rule that one out. It's okay. You don't have to worry about, oh, it's going to ruin my aromaticity. Don't worry about that. It's not the case. It's not here because it's hypothetical. And one last thing, sometimes whenever you see on the exams, on the practice exams, you'll see something that says, oh, basic nitrogens. In that case, what it's referring to is the sp3 nitrogens, right? So the ones that are basic essentially cannot contribute to resonance. So what that would look like is, say for example, you had like a molecule like this, and oh, it's like, say oxygen. Then we have another one where it's like, okay, so like in this case. Now, in the sp3s, the basic nitrogens refer to sp3 nitrogens. So 1, 2, 1, 2, and then 3. Oh, sorry, that counts that. Yeah. Okay, good. All right. So the sp3 nitrogens. So just in terms of hybridization, 1, 2, 3, 3 bonds, and then 1 lone pair. 4, sp3, you just kind of go off of that. These guys cannot contribute to resonance at all, okay? In this case, for example, this guy will not contribute to resonance because he's far away. So this guy won't actually do anything. He can't contribute to resonance, therefore he is basic. This guy can. This guy can actually resonate inward and cause more resonance, okay? This can also work with something that, like, let's say here, so here, no, I'm sorry, no, it cannot. Okay, no. So it just has to be morally direct, I guess. Just kind of adjacent. But the key is, though, it does not participate in resonance, and it's usually far away from a ketone or any kind of group that can resonate. That will just be the sp3 carbons. The sp2s, those are not basic, so therefore, like, these would be an sp2. But the sp3 carbons, the ones that do not resonate and they do not have delocalized electrons, they're localized on the nitrogen, therefore are considered sp3. Basic nitrogens. So sometimes you'll see that on the exam. So that should be the basics of acidity, aromaticity. The nomenclature, legitimately, like, that's just a memorization thing. I couldn't really give you any tips on how to do that or explanations. That is just simply memorization. So yeah, that concludes week 5.